Hope everybody's having a good day today. So today I wanted to talk to you guys about utilizing GIS to streamline noise analyses. A lot of people are probably wondering what a noise analysis even is. So basically, my name is Jarrett. I'm a noise and GIS analyst for Gannett Fleming. I work a lot with geodecisions, and what I do for a living is design basically noise mitigation for highway systems, rail systems, basically anything that can create noise for that matter. So what exactly is a noise analysis? Noise analyses are conducted to basically document the change from an existing noise condition to whatever the future implementation of a project is going to be and how that's going to change noise levels moving forward. So that could be, oftentimes in my line of work, consists of highway improvements, and I'm not talking, restriping roads. I'm talking widening roads, like physically altering the horizontal alignment of a system. So, if they're putting in rail or even something as small as a substation upgrade. So, a lot of times they upgrade their transformers, and these transformers, believe it or not, have certain noise thresholds that, if you're a community nearby, you don't want to hear a buzzing coming from these transformers. And over time, people want some sort of mitigation put in place to, counteract the noise that's being coming into play with these new improvements. So a lot of times they consist of noise barriers or some sort of system to muffle the sound. And I think that's a fitting picture. Oftentimes when I go to public involvement meetings, a lot of what I deal with is the public being mad about, construction noise, or, if you're going to increase, the highway from 4 to 6 lanes, it's going to cause a lot more sound for us. So we do sound studies to document, what the existing noise levels are in a certain noise environment and how the future implementation of projects are going to affect them, and how we can help design mitigation measures to reduce these types of impacts. So what I do in noise is I build models using GIS to get ultimately into a program called the traffic noise model. This is the beautiful beast that you see here. It's super detailed, as you can tell, and I mean that sarcastically. This was designed in the early 90s, but is the only federally approved noise program that we have to predict highway traffic noise. God bless you. This can be used for other instances. There's different ways that the NCHRP has figured out how to model different things in this program other than just highway traffic noise, but the predominant use of this program is highway traffic noise. As you can see, there's different elements that go into this model. So obviously you're seeing a roadway network there, building barriers. Typically the various DOTs want to capture the front facade of a building to see how that can affect shielding for receptors behind it. So if you look at the black dots that are on the screen right now, those are considered receptors, or a place where we place a hypothetical site to see what the noise levels would be there. And that's typically basically somebody's active outdoor use area. So, a playground, a school, somebody's backyard, a deck, something like that. And we predict future highway traffic noise using those receptors. Typically, it's reading at a 5-foot height of like an average person. So what this model does is it takes into account the 3D attributes that we put into it to design these roads, building barriers, receptors. The green stuff you see is terrain lines, trying to capture anything of significant cut fill for future roadways. And the program runs an algorithm to interpolate, a certain noise level predicted with these future impacts. Additionally, on these roads, they carry a certain traffic volume that we receive from traffic engineers, and we apply those volumes to these roadways, and they have certain energy levels associated with them. And that energy level is also built into the algorithm it takes into account, like I said, the 3D attributes that are between the receptor and the roadway, and then how that will affect, obviously, the noise degradation as it travels. Here's a side view of the program. We code the building barrier heights to a certain top elevation. So, like I said, it's not the prettiest program to use, but it's the only one that is federally approved and that we're mandated to use. And here's another picture of an area where we're designing a noise barrier for a community, just kind of a side shot of that. And before all of this started and we started using GIS to do this, there was a little bit dated methods of constructing these. So people would snap lines to stationing, and there would be a lot of back and forth as to, we would have to read through different cross-section files and manually jot down information for the elevations of the roadways and stuff like that. And then we would end up physically drawing this in the program you see here, and we would have to manually enter all of the X, Y, Z's into this program. So, what this ended up happening, it was a very time-consuming process for consultants to do. It opened up a much larger room for error because nobody's perfect. Copy and pasting errors. You snap so many points, you lose track of where you're at. And basically, when I'm talking about snapping points, is we would get engineering files from engineers for the proposed roadway, and you would basically drop a point at each station mark in the center of the roadway because the model is designed to represent the center lane of a travel. And from that, you would then go into this beautiful cross-section file that you would get, and you would have to see, okay, at station 17 plus 00, our elevation is 25.99. And you would do this for all the points that you snapped. So over time, this gets pretty cumbersome. I mean, if you get a 12-mile stretch of roadway, this can take, a couple weeks. So moving forward with that, some processes tended to evolve more, and, certain folks like myself who started doing noise and had more of an interest in GIS found that GIS had a lot more opportunity to streamline these things. So what we ended up starting to do is we would digitize a feature class for each input that the program took. I just want to say that T&M takes DXF files. So what we would do is we would digitize our roadways and everything based on the design files in GIS. And then we would use certain tools in GIS, which I'll get to later, to 3D these features based on the engineering files that we received from the engineering department. And let me just say that I will add a disclaimer moving forward. I don't know if anybody was part of the PLC discussion this morning, but sometimes we have to use existing contours, and based on discussions this morning, it sounds like we need to start adding a disclaimer to that. But anyway, so we would use this data and 3D it and basically bring it into this model as a DXF file. So this is just a screen capture of, I think, one of my projects from Arc Desktop. It's basically trying to capture the fronts of buildings based on aerials. And then there's the green dots are all noise receptors, and they're all coded at different heights. Some of these buildings happen to be multi-story dwellings, so the heights are a little different in certain areas. So this is kind of the process that we would go about. And I know most people probably wonder, can we use different data sets that the county offers? And we can, but a lot of that would have to be heavily modified because, when you're getting structures, you're getting them as polygons, and the way that the DOT wants to see certain things is, if you can see those red lines in there, the fronts of the buildings, they don't want the back. They just only want that front piece and the sides. So there would be a lot of post-processing to do there. So a lot of it is hand digitized in. And this is a surface file that we get from engineers. So when they go out and they do their surveying, we typically get a TIN file from them to try to get an idea of the existing ground out there or the proposed ground. But what you're seeing here is the TIN files that we receive in a Bentley software program. So GeoPack, MicroStation, Inroads, they all are made up of these triangulated features. But for us to use this in GIS, GIS doesn't like the Bentley software programs, and they don't play nicely. So we found a workaround where we can convert these TIN files to a land XML using GIS, or excuse me, using any of the MicroStation or Bentley packages. And then from there, we can import the land XML into a GIS framework, whether or not it's Arc Pro or Arc Desktop, but you would need to have a 3D analyst license. I personally like to use Arc Pro when I do this, just because of the 64-bit processing, everything kind of moves a lot quicker. And then our output would look something like this. So you have your TIN file, and then I just provided a more zoomed in version of that. So that's kind of how we get our 3D files into GIS. And then a lot of times when we receive engineering files, the way that they do this is, I'm not sure if everybody's familiar with the Y lines and the L lines, but the main lines of the highway network, let's just say I-40 would be considered the L line. And for a whole project that's 12 miles long, they might not give us a whole TIN file that would cover that 12 miles. So they might give us one that covers the first 3, and then 3 through 6. So what we end up having to do is we get all these different TIN files, but for our work, when we digitize lines, and we use the Interpolate Shape tool in 3D, if any of those lines fall outside of a particular TIN, if any vertex on that line falls outside of the TIN that you're using to 3D the line, the whole line doesn't get 3D'd at all. So we like to combine all the TIN files we get from the engineers into one. And the only workaround that I've found to do that so far is by converting all of these TIN files to a land XML, creating their own separate TIN file for each, and then from there, using the TIN node tool, which basically takes that TIN file and will condense all of that data into a point source data, kind of like you're seeing here. So it's basically taking all the data that we have for that specific TIN file, creating a ton of points from it, and displaying it like this. Then from there, we can use the Create TIN tool and add multiple TIN nodes together to create something like this. So originally what you're seeing here, if you're looking at the vertical lines between them, these were all individual TIN files. After I had converted these TIN files to their own TIN and then converted them to TIN nodes and then stitched them all back together, this is what we get. And I can design a roadway network for this entire stretch and only have to 3D at one time instead of having to have certain breaks in the road and then stitch things back together in our noise program. So this is it sounds like it's a lot of work, and it is up front, but the headache that it saves you down the road and the accuracy that it provides is much more efficient use of our time than trying to go back into the program that we use and stitch everything back together. So yes, the individual TIN files are more labor intensive for the 3Ding process. Like I said, we would have to break roads and stuff like that. But having a combined one is probably equally as time consuming, but that time up front is saved on the back end in the noise analysis process. So after we 3D our roadways, we get a file that looks like this. What I'm using here is ArcScene to make sure that everything after I 3D the lines looks good to me. Basically, sometimes there could be an issue with the TIN file, and you can get something that looks like this. In specific instances, we have TIN files that we get from engineers that might not capture a bridge deck. This is a file that I physically altered just for this presentation, but so all those roadways there where you see that dive down, it might not have the elevation for the roadway there. And these are things that we check for in ArcScene before we get it into T&M. That way we can make sure that once we have the model good to go, that there's no issues, because this could, depending on where you're at in the model, this could drastically affect how your noise is, because it's assuming that cars are going at a certain grade and then all of a sudden jumping down 20 feet. So another use of GIS after we're done our whole modeling process, we get certain noise impacts based on whichever DOT we're working on and whichever their criteria is. I think a heavy use in GIS for us as well is cartography. And GIS has helped us streamline a lot of cut sheet mapping for a lot of projects, because I know before, I've talked to folks who have used MicroStation and other mapping services to create figures, and they're doing one figure per area, whereas if I use something like data-driven pages in GIS, I can go through a 12-mile stretch of corridor and have each polygon represent a certain cut sheet and kind of breeze through everything pretty quick. And I think it also helps us use GIS as a tool to try to convey to the public, what we're seeing in a noise model. Because most people, we go to a public meeting and they're like, I don't know what this means. I don't know where noise walls are going to go. And this allows us to basically show them and try to explain to them, what we're seeing in the model and on the figures. So other uses, we work on a lot of design build projects. There's a lot of back and forth with contractors. So earlier, in this morning's meeting about PLC, it's really important that we make sure where we're putting things are in the exact location in our models, because that's what they're going to build. And a lot of times the contractor, doesn't know what type of form of data we're going and dealing with. So they'll give us, XY data. And let's just say for a noise wall alignment that they want to put in, we'll take an XY data, Excel spreadsheet, bring it right into GIS, export it to the T&M, and we're good to go. There's other forms of use that we have here. One of the other important ones that I want to point out is exporting your desktop or your MXD as a KMZ file, because not everybody has GIS. So it's really easy to share what you're seeing in your program with people who don't have a GIS license, and vice versa. You can bring files in that you get from consultants or from the DOT straight into GIS as a layer. Now, GIS moving forward, they're trying to revamp the traffic noise model 3.0 or the 2.5 to 3.0, and some of my colleagues who work at GeoDecisions have been very instrumental in that development process. And it's not federally approved yet, but they're working on a GIS GUI that you could basically add this toolbar directly to your Arc desktop window or your MXD, and you would be able to design everything within one solid geodatabase and not have to export files to a DXF or anything like that. You'd be able to just bring that geodatabase straight into T&M, which would be a huge time saver for us, and I'm sure for other people who aren't engineers that do noise analyses. It would save them some time, because I think GIS is super user friendly compared to MicroStation or Inroads or GeoPack. So I think this is a huge step in the right direction. But like I said, it's been in discussion for a couple years now, so I don't know when that would get approved. But the new version has the ability to stream Esri imagery and street maps, which the program that we use right now, all we had is that pretty white background, and you can't really do much about that. So that's basically it for future uses. And I don't know if anybody has any questions, but I'll do my best to answer. Yep.
So what's the output of the models? If those ones that make it assign some sort of a noise value?
So each one of those receptor points does get assigned a decibel level value. And then depending on that decibel level value, they're all reported on in the noise report that we provide the DOT or the client. And depending on the threshold of, let's just say if it's 66 decibels, that would be considered an impact. And that's something that DOT wants to know, and they want to know where the location of that is. And ultimately what that helps them do is try to figure out where they're going to put, let's just say, a noise barrier in the future, and, how they can plan for that. Is the noise barrier going to be 20 feet high? Because this program allows us to basically run a noise wall at different heights and see, based on the ground of that terrain for that noise wall and the panel height incorporated, how that can reduce the sound. So when we run the models with a noise wall in there, it basically takes the sound without the wall and then the sound with the wall. And then when we perturbate the panels up and down, and we can kind of get a gauge on how big that wall is going to be. So it's a good tool for DOT. The traffic noise program, the traffic noise model is, but I think the use of GIS and all of that and the accuracy that it can help provide is a lot better than what some folks are using. Mm-hmm.
You don't specify types of vehicles.
Oh, no, we do. We specify between autos, so like your standard car, your medium trucks, so something with around like 3 axles, let's say. And then you have your heavy trucks like your semis, and then they have motorcycles and buses. And each one of those classifications are assigned a different energy level. And then with that, obviously, that's all incorporated into the algorithm that basically draws triangles from the roadway noise source to the receptors, and then everything in between, it would take into account, like, okay, this terrain line is, providing shielding, let's just say like a berm, and that's going to block X amount of noise. So that's basically what the program does. So for us to have the ability to have really good GIS data and look at all this from that side of things, because I think GIS is a very good visual tool when you're looking at TIN files and contours and stuff. I know not all of it is actually PLC certified, but sometimes it's better than going with a 1980s design file that somebody came up with, and that's what you're kind of left to use. So anything outside of that, we're trying to make up the best we can do. So, anybody? Yeah.
So here you're describing the building doing that, like drawing lines based on the work density.
Mm-hmm.
Is there any conflict, like issue with using a shape that has the building footprint on it?
There's not an issue with it. We would just have to edit it. So a lot of DOTs, they only want to see, let's just, if you think about the letter C, that's the only piece of the building that they want to see. So you would have to end up trimming off the back end of that. Like, so if the footprint is a polygon, you would have to trim off the back end of all of that.
Would it affect the noise?
The noise, so when you put those red lines in there that represent the face of the building, they actually go in as a line, and they're not able to go in as a polygon, which is one of the flaws of the model. So that's why we put it in that way. So if T&M 3.0 progresses to the point that it could accept something like that, that would be a huge time save for us.
With the technology, in the future, more electrical cars, so even if you don't do something at noise level, highway traffic could go down.
I don't know I know this noise model does not incorporate, like I said, it's early 90s, and it's not been touched. So I know it doesn't include any sort of electric vehicles and how that would affect noise. Caitlin, do you know if T&M 3 does? I don't think the new one does, but it's definitely something that, I think probably they would look at that from a percentage. What percentage of vehicle users are using a hybrid vehicle versus what percentage are straight gas. And I think that they'd probably go with the more dominant one for now, they want to basically look at a worst case scenario. So they don't want the public to come back and say, why did you guys use 50% electric cars? Because they don't make as much noise. We want a noise wall. So we try to look at it from a worst case scenario. Anybody else? Well, thank you for giving me the opportunity to present.